Welcome, my friend. You found your way to the Sleepy Scientist, a quiet corner of the internet where curiosity moves at a gentle pace and the stars above are always within reach. I'm so glad you're here. Before we set off on tonight's journey, may I ask, where in the world are you watching from? I always find it fascinating to imagine this little community stretching across continents, connected by a shared moment under the same sky. If you're new here, I'd be grateful if you could give the video a like and consider subscribing so you can join us again for more gentle explorations of the universe. And if you'd like to know the moment our next Sleepy Science adventure drifts into your feed, you can tap the little notification bell. To those who have already subscribed, thank you for being part of this strange and wonderful experiment in bedtime science. Now, I do hope this video isn't too interesting and ends up keeping you awake. Though if it does, at least you'll drift off with a few more facts in your mind than you had when you pressed play. It's the kind of problem I'm not entirely sure I should apologise for. Tonight, we're going to take a slow, starlit voyage through our galaxy, the Milky Way. But here's the question I'd like to begin with. If we can only ever see our home from the inside, how can we truly know what it looks like? The Milky Way is not just a backdrop to our lives. Is the very stage upon which all of human history, all of life, and every shimmering moment has played out. We live within its vast embrace, yet most of it remains invisible to our eyes, hidden behind clouds of cosmic dust and the sheer, dizzying scale of space itself. In this journey we will drift slowly from the familiar to the far-flung. We'll wander the spiral arms, linger among newborn stars, cross the quiet halo and dip into the mysterious heart of the galaxy where a supermassive black hole resides. Along the way, we'll meet the many kinds of stars that call this galaxy home, the clusters they form, and the gas and dust that both obscures and creates them. We will explore not only what the Milky Way is made of, but also how we know what we know, the careful observations, the patient measurements, and the ingenuity that allow us to map something so impossibly large from our tiny vantage point. And perhaps we will think about what this galaxy means to us, culturally, scientifically, and personally, as the only cosmic neighbourhood we've ever known. So get comfortable, let your thoughts drift like starlight through the darkness, and join me as we begin our slow voyage through the Milky Way. If you could step far enough away from our galaxy, far, far beyond the pull of its stars, you would see it as a soft, glowing whirlpool hanging in the dark. From that impossible vantage point, the Milky Way would reveal itself as a vast barred spiral, a flattened disk of stars wrapped around a bright central bulge, with long arms curling gracefully outward like the petals of a cosmic flower. It is a place of both order and chaos, where patterns emerge from countless random motions, and where light from billions of suns blends into a single pale shimmer. The scale of it is almost absurd. From end to end, the Milky Way stretches for roughly 100,000 light-years. A light-year is the distance light can travel in 1 year, about 9.5 trillion kilometres, which means the galaxy is wide enough that even at light speed, a trip from one side to the other would take longer than the entire history of human civilization by a factor so large it makes numbers feel slightly ridiculous. If our sun were the size of a single grain of sand, the galaxy would still be larger than the span of entire continents. Its shape is not simply a neat spiral drawn in space. At the heart lies a bar-shaped cluster of stars running through the central bulge. From the ends of that bar the spiral arms unwind, rich with gas, dust, and newly formed stars. The main arms, Perseus, Scutum Centaurus, Norma, and Sagittarius Carina, sweep outward in gentle arcs. Between them lie shorter segments and spurs, like smaller branches in a great cosmic tree. From above, it would look like an artist's slow brushstroke through the night, spiralling ever outward. We, rather modestly, do not occupy one of the grand, sweeping main arms. Instead, our solar system sits in a quieter neighbourhood, a smaller spur of stars called the Orion Arm, or sometimes the Orion Spur. This spur lies between two larger arms, the Sagittarius arm closer to the galactic centre and the Perseus arm farther out toward the edge. Our location is, in many ways, rather fortunate. It is calm enough to avoid the more chaotic regions of intense star formation that might bathe worlds in harmful radiation, but close enough to the action that we're surrounded by a rich view of stellar life. From our position, we are roughly 27,000 light-years away from the galactic centre. That might not sound too bad. After all, in everyday human terms, 27,000 of anything is not an unthinkable number. But in space, it is an immense gulf. If you could somehow travel at the speed of light, which you cannot unless you are light, it would still take you 27 millennia to get there. For comparison, 27,000 years ago, the last ice age was in full swing, and mammoths were still trudging across the Earth. This vastness also means that our nearest stellar neighbours are anything but next door. The closest star system to our Sun, Alpha Centauri, is more than 4 light-years away, around 40 trillion kilometres. Even with our fastest spacecraft, it would take tens of thousands of years to get there. In galactic terms, that is like saying the house next door is actually somewhere past the edge of the horizon. And to get there, you would need to walk for multiple human lifetimes without stopping. The Milky Way's disk is not perfectly flat. It has a gentle warp, as though the whole galaxy has been very slowly twisted over time. This warp is thought to be caused by gravitational interactions with neighbouring satellite galaxies, smaller companions that orbit the Milky Way much as the Moon orbits Earth. The disk is also surprisingly thin compared to its width, like a cosmic pancake with a fluffy central mound. Most of the galaxy's stars, gas and dust lie within a disk only a few thousand light-years thick, while a halo of old stars and dark matter surrounds it in all directions. This halo is the galaxy's ghostly outer boundary, and though it is far less dense than the disk, it holds important clues about the Milky Way's history. Within it are ancient globular clusters, spherical swarms of stars that have been orbiting the galaxy for billions of years, predating much of the structure we see today. These clusters drift far above and below the galactic plane, marking the Milky Way's oldest stellar population. The sheer number of stars in the galaxy is staggering. Estimates suggest there are at least 100 billion of them, and possibly as many as 400 billion. And yet the space between them is so vast that, on average, the nearest star to any given star is several light-years away. In a way, the Milky Way is more emptiness than substance, an enormous expanse in which islands of light float in oceans of darkness. From our small patch within the Orion Arm, we cannot see the Milky Way as an outsider would. Instead, we experience it from within, as a river of pale light stretching across the night sky. That light is not the glow of a single object, but the combined radiance of countless stars too distant to resolve individually, their light blending into a misty band. It is one of the few things in nature that is both an intimate part of our world and unimaginably far beyond it. Understanding the Milky Way's shape, size and structure is like trying to sketch the floor plan of a house while standing inside a single room with no windows. We must piece together the whole from small glimpses, relying on careful measurement, the behaviour of light and the slow mapping of the sky. Every star's position, every swirl of gas, every faint whisper of radio waves tells us a little more about the home we live in. A home so vast that our entire civilization is a barely noticeable flicker within one of its countless stars. And yet, despite its size, the Milky Way is still just one galaxy among billions in the universe. From the outside, it might not seem particularly special, but from here, inside it, it is everything. The stage, the scenery, and the quiet backdrop to our every moment. If you could see the Milky Way from far above, you would notice it does not form a perfect pinwheel of evenly curved arms. Instead, there is something striking at its centre, a bright bar of stars cutting across the bulge from which the great spiral arms unfurl. This makes the Milky Way what astronomers call a barred spiral galaxy. The bar is not just a decorative feature, it is thought to act like a gravitational engine, channeling gas inward toward the centre, feeding both new star formation and the activity around the supermassive black hole that resides there. In turn, the bar's rotation helps shape and maintain the galaxy's spiral pattern, guiding material into the arms like water flowing into a whirlpool. The spiral arms themselves are not solid structures, the way an actual whirlpool's currents might be. They are regions where stars and gas are more densely packed than in the surrounding space, but individual stars do not stay in the same arm forever. Instead, the arms are more like traffic jams on a cosmic scale. Cars in a traffic jam move in and out, but the jam itself persists in roughly the same place. Similarly, stars, gas and dust pass through the spiral arms, slowed and compressed by a kind of gravitational wave pattern known as a density wave. This density wave theory explains why the spiral arms are the cradles of so many young stars. As gas clouds drift into an arm, the added pressure from the denser environment causes them to collapse, igniting new stars. The brightest and most massive of these stars live fast and die young, burning through their fuel in only a few million years. Because they do not have time to wander far from where they were born, these luminous giants light up the spiral arms, tracing their curves for us to see from within. Meanwhile, older and smaller stars drift out of the arms, continuing their slow orbits around the galactic centre. If we could take a slow and unhurried tour from arm to arm, starting near our own Orion arm, we would find each one has its own character. The Orion arm is more of a spur than a full arm, but it is by no means unremarkable. It contains not only our Sun and solar system, but also familiar landmarks of the night sky, such as the Orion Nebula and the Pleiades star cluster. This is the view we know best, but in cosmic terms it is just a small side street off a grand galactic boulevard. Move inward toward the galactic centre, and you encounter the Sagittarius arm. This arm is a rich hub of star formation, filled with bright nebulae like the Lagoon Nebula and the Trifid Nebula, as well as star clusters only a few million years old. Its close proximity to the dense central regions means there is a steady supply of gas being funneled into it, giving it a vibrant, energetic quality. From our perspective on Earth, looking through the Sagittarius arm is one of the best ways to see deep into the Milky Way's core. Travelling outward from our spur instead, you would cross the gap to the Perseus arm. This is one of the Milky Way's two main arms, stretching in a long, graceful curve that is home to some of the galaxy's largest star-forming complexes. The Perseus arm is rich in both young, massive stars and the glowing clouds of hydrogen gas that mark active stellar nurseries. Radio telescopes have traced giant molecular clouds here, each containing enough material to form thousands of new stars. It is the galactic equivalent of an agricultural heartland, a place where new generations are continually being sown and grown. Farther in toward the galactic centre lies the Scutum Centaurus arm, another of the main arms, sweeping from near the bar outward across much of the galaxy's inner disk. It is home to some of the largest and brightest star clusters known in the Milky Way, including Westerlund 1, a dense collection of massive stars packed into a relatively small region. The Scutum Centaurus arm is so rich in luminous stars that it outshines many other parts of the galaxy, though from our position in the Orion spur it is partly veiled by clouds of interstellar dust. Beyond that lies the Norma arm, tucked deep within the inner regions of the galaxy. This arm is harder to observe directly because we view it through thick curtains of gas and dust, but infrared and radio observations reveal its wealth of young stars and its role as one of the key structural components of the Milky Way. In many ways, it is a reminder that our view of the galaxy is always partial. There are wonders we know exist but can never fully see with human eyes. What makes this spiral structure so remarkable is that it is not a fixed arrangement carved in stone, but a pattern that persists over billions of years despite the motion of countless individual stars. The entire galaxy rotates. The Sun itself orbits the galactic centre once every 225 million years or so, but the arms remain as stable, overarching features. This balance between motion and structure gives the Milky Way its elegance, a grace that is both dynamic and enduring. The bar at the centre, the arms winding outward, and the spaces between them all work together to define the Milky Way's shape. The spaces between the arms are not empty. They are filled with stars and sometimes even faint, less active clouds of gas. But the arms are where the galaxy shows off, where it concentrates its most photogenic displays of glowing gas and brilliant, short-lived stars. And yet, despite the beauty of the arms, from the inside they can be surprisingly difficult to recognize. On Earth, when we look up at the Milky Way's band across the night sky, we are seeing along the plane of the galaxy a dense concentration of stars and dust that hides the exact arrangement of the arms. Mapping them has been like trying to chart the streets of a city while standing in the middle of one. We rely on the positions of known objects, on measurements of their distances and motions, and on the faint whispers of radio waves from hydrogen atoms spread through space. Piece by piece, these clues have allowed astronomers to outline the grand spiral form we cannot see directly. In the end, the Milky Way's spiral is more than just a pretty shape. It is the pattern of its life. The arms are where stars are born, where the galaxy's raw materials are recycled into new generations, and where light and colour spill most vividly into the cosmic night. To drift from one arm to another would be to pass through regions of quiet starlight into bustling star-forming hubs and back again, each with its own rhythm, each a part of the galaxy's endless slow-turning dance. At the heart of the Milky Way lies a region unlike anywhere else in our galaxy, the galactic centre. From our position in the Orion Arm, it is hidden behind vast curtains of dust and gas, invisible to our eyes even on the clearest night. Yet astronomers have peered through those curtains using infrared and radio waves, revealing a place of staggering density, ancient stars and gravitational forces so extreme they defy everyday experience. The galactic centre is dominated by a swollen bulge of stars, a dense football-shaped concentration that extends thousands of light-years above and below the galactic plane. This bulge contains some of the oldest stars in the Milky Way, many of them low in heavy elements, which suggests they formed in the galaxy's earliest days. The sheer number of stars here is hard to grasp. Imagine the night sky if every star you could see was suddenly packed into a space a fraction of its current size. From within the bulge, the sky would be so crowded with light that true darkness might be rare, the combined glow of millions of suns turning night into a perpetual dim twilight. But it is not just a stellar crowd. Nestled deep within this throng is perhaps the most intriguing resident of all, Sagittarius. A star, the supermassive black hole at the centre of the Milky Way. Its name comes from its position in the sky, in the direction of the constellation Sagittarius, and the A star is an astronomer's way of marking it as something special. Despite its immense mass, about 4 million times that of our Sun, Sagittarius A is surprisingly quiet most of the time, radiating only faintly compared to the raging, matter-devouring black holes at the centres of some other galaxies. We cannot see Sagittarius A star directly, because no light can escape its grasp, but its presence is revealed through its influence on the stars around it. In the late 20th century, astronomers began tracking a group of stars very close to the galactic centre. These stars, known as the S-stars, were seen whipping around an unseen point at extraordinary speeds, some completing full orbits in just over a decade. Only an object with the mass of millions of suns packed into a space no larger than our solar system could explain such motion, and that object could only be a black hole. One star in particular, called S2, has been a star of the show, so to speak. It swings in closer to Sagittarius A star than Pluto is to our Sun, reaching speeds of thousands of kilometers per second. At those distances, the gravitational pull is so intense that the predictions of Einstein's general theory of relativity come into play. In fact, careful observation of S2's path has confirmed subtle effects predicted by relativity, such as the way light is redshifted by strong gravity. These stars are not just beautiful, they are living laboratories for testing our understanding of the universe. The environment near the galactic centre is extreme in almost every sense. The density of stars increases dramatically as you approach the middle, meaning stellar encounters are far more common. Massive young stars can be found here as well, even though it might seem like the last place you would expect them. The region is turbulent, bathed in intense radiation, and crowded with gravitational influences. Their very presence suggests that star formation can occur in conditions far harsher than those we find in the galaxy's quieter suburbs. Gas and dust clouds swirl through the centre, occasionally falling toward the black hole. When enough material gets close, it forms an accretion disk, a whirling maelstrom of gas spiralling inward, heating up to millions of degrees and emitting bursts of energy. These feeding events are sporadic for Sagittarius A, but they remind us that even a relatively calm, supermassive black hole is not entirely dormant. Astronomers have also found evidence of massive outflows from the galactic centre in the past, such as the Fermi bubbles, enormous lobes of high-energy radiation extending tens of thousands of light-years above and below the disk, possibly caused by ancient eruptions from Sagittarius A star. There is also a population of enigmatic objects here, some of which appear to blur the line between stars and gas clouds. They may be stars enveloped in thick shrouds of dust, or something stranger still. In the gravitational chaos near Sagittarius A star, matter can be stretched and heated to the point where familiar categories break down. Even with our best instruments, the galactic centre remains a place of mystery. We can trace the orbits of stars and map the distribution of gas, but the sheer density of material makes it difficult to get a clear picture. It is a reminder that our view is always from within, peering through a crowded, turbulent foreground toward the hidden core of our home. If you could stand safely on a stable platform close to Sagittarius A star, a purely hypothetical notion, since gravity there would tear apart anything solid, the sky would be unlike anything imaginable. Stars would whirl past in fast arcs, distorted by gravitational lensing into strange smears and loops of light. The black hole itself would not appear as a hole so much as a dark circular void, framed by a glowing ring where light is bent and captured from the surrounding stars. The scale and speed of motion would make the whole scene feel more like the inside of some vast cosmic machine than the serene night skies we know. And yet, for all its extremes, the galactic centre is part of the same galaxy that gently cradles our sun. The pull of Sagittarius A star reaches us even here, guiding the sun and its planets in their long, slow orbit. From our quiet vantage point, it is easy to forget that at the core of our galaxy lies a place where space and time are bent into shapes that defy everyday intuition. A reminder that the Milky Way is as much a place of extremes as it is of quiet beauty. The Milky Way is not just a collection of stars. It is a vast, glittering archive of every kind of star nature has ever devised. From tiny, cool red dwarfs to enormous short-lived supergiants, from the steady hum of main-sequence stars to the exotic remnants of dead suns, our galaxy contains a full cast of stellar characters, each with its own story. If you could float through the galaxy without hurry, you might pass by millions of stars in every shade and size, their light ranging from deep crimson to piercing blue-white. Most stars you encountered would seem quiet and unassuming, the cosmic equivalent of people who keep to themselves and rarely make headlines. But scattered among them would be rare giants, brilliant and unpredictable, their lives burning fast and ending with spectacular finales. Astronomers often sort stars using the Hertzsprung-Russell diagram, a kind of map that plots them according to brightness and surface temperature. Most stars, including our Sun, fall along a band called the main sequence. Here, stars are in the stable phase of their lives, steadily fusing hydrogen into helium in their cores. The position of a star on this sequence depends largely on its mass. Heavier stars are hotter, brighter, and bluer, while lighter stars are cooler, dimmer, and redder. The smallest and most common of these are the red dwarfs. They are so faint that none are visible to the naked eye from Earth, yet they make up the overwhelming majority of the Milky Way's stellar population. A red dwarf's life is one of quiet efficiency. Because they burn their fuel slowly, they can shine for trillions of years, far longer than the current age of the universe. In a sense, they are the ultimate survivors, small, steady, and built to last. If the galaxy had a background soundtrack, it would be the faint, enduring hum of red dwarfs. At the other end of the main sequence are the massive hot blue stars. These luminous giants are rare but impossible to miss. Their intense light can travel great distances, and they often dominate the regions around them. But their brilliance comes at a cost. They burn through their nuclear fuel at a furious rate, living only a few million years before running out and ending their lives in spectacular supernova explosions. For a galaxy, these stars are more like dazzling fireworks than long-burning candles. Between these extremes lies a wide variety of stellar types: yellow dwarfs like the Sun, orange dwarfs slightly cooler and dimmer, and white stars that burn hotter. Each one will spend the majority of its life on the main sequence, in a long period of balance between the outward pressure of fusion and the inward pull of gravity. This balance is so stable that, from our perspective, stars in this stage seem almost eternal. But not all stars are content to remain in the main sequence forever. When a star exhausts the hydrogen in its core, it begins to change. For stars like the Sun, this means swelling into a red giant, a cooler but much larger star whose outer layers expand dramatically. A red giant can be hundreds of times wider than the Sun, its surface glowing with a soft orange-red light. The atmosphere becomes so distended that the outer layers can drift away into space, enriching the galaxy with heavier elements forged in the star's core. More massive stars follow a different path. When their hydrogen runs out, they move rapidly through a series of fusion stages, creating heavier and heavier elements until they reach iron, a dead end for energy production. At that point, the core collapses under its own gravity, triggering a supernova. The aftermath can leave behind either a neutron star, a city-sized object so dense that a teaspoon of its material would weigh billions of tons, or for the most massive stars, a black hole. Neutron stars are among the strangest objects in the galaxy. Some spin rapidly, sweeping beams of radiation across space like lighthouse beacons. These pulsars can be detected from thousands of light years away, their signals as regular as the ticking of a clock. Others are magnetars, with magnetic fields so intense they could erase the data on every credit card on Earth from a distance of several 100,000 kilometers. Not that they are in any rush to do so. Supergiants are the most flamboyant of all stars. These immense bright behemoths can be tens to hundreds of times the mass of the Sun and thousands of times more luminous. Betelgeuse, in the constellation Orion, is a well-known red supergiant, large enough that if placed in the centre of our solar system, its surface would extend past the orbit of Mars. Blue supergiants, like Rigel, are equally impressive but live even shorter lives. Their powerful stellar winds can shape the surrounding space, carving cavities in interstellar gas and creating spectacular nebulae when they eventually explode. There are also the stellar elders, white dwarfs, the remnants of sun-like stars that have shed their outer layers and no longer fuse elements in their cores. These dense, Earth-sized objects slowly cool over billions of years, fading into black dwarfs, a stage the universe has not yet reached, because it is not old enough for any white dwarf to have cooled that far. Every type of star plays a role in the Milky Way's ecology. Massive stars seed the galaxy with heavy elements in their violent deaths, enriching the gas from which new stars and planets will form. Smaller stars preserve those elements over long timescales, acting as stable hosts for planetary systems. The constant cycle of birth, life, and death ensures that the galaxy remains a dynamic, evolving place rather than a static one. If you were drifting through space, moving slowly from one star to the next, you might notice patterns in their distribution. Clusters of hot young stars often lie near regions of active star formation, glowing against the dark backdrop of molecular clouds. Farther away in the quieter reaches, the view is dominated by older, cooler stars. Red dwarfs and orange dwarfs, their light softer and steadier. This balance between the rare brilliance of giants and the quiet persistence of dwarfs gives the Milky Way its character. Perhaps the most humbling realization is that the stars we can see with the naked eye represent only a tiny fraction of those that exist. The vast majority, the countless red dwarfs scattered throughout the galaxy, shine too faintly for us to notice without a telescope. And yet, in sheer number, they dominate, forming the unseen backbone of the Milky Way's stellar population. They may not dazzle the eye, but their quiet endurance means they will still be here long after the last supergiant has burned out, their light continuing to fill the galaxy's night for trillions of years to come. Among the most beautiful and mysterious places in the Milky Way are the stellar nurseries, vast clouds of gas and dust where new stars are quietly taking shape. These regions are not hurried. The process of creating a star can take millions of years, unfolding with a patience that only the cosmos can manage. Seen through a telescope, these nurseries often appear as glowing, intricately patterned nebulae, each with its own character and history. Nebulae are essentially enormous interstellar clouds, often dozens or even hundreds of light years across. They are composed mainly of hydrogen gas, with smaller amounts of helium and traces of heavier elements. Mixed in with the gas is fine dust, tiny grains of carbon and silicates that scatter and absorb light. This dust is not like the kind that gathers under your bed. Each particle is far smaller than a grain of sand, yet together they can block the light of distant stars, creating dark patches and shapes against the glowing background of the galaxy. One of the most famous stellar nurseries is the Orion Nebula, a bright patch in the sword of the constellation Orion that can be seen with the naked eye from Earth. Just over 1,300 light-years away, it is the closest region of massive star formation to our solar system. Within its glowing clouds lies a cluster of young, hot stars known as the trapezium, whose intense radiation lights up the surrounding gas. The Orion Nebula is like a cosmic classroom, allowing astronomers to study the process of star birth in detail. Its filaments and knots of gas reveal where gravity is slowly drawing material together, where new stars are forming, and where stellar winds from older siblings are shaping the landscape for the next generation. Farther away, in the southern skies, lies the Carina Nebula, one of the largest and most active star-forming regions in the Milky Way. Stretching over 300 light-years across, it contains some of the most massive and luminous stars known, including the volatile giant Eta Carinae. The Carina Nebula is a turbulent place, with powerful stellar winds and supernova explosions sculpting its clouds into dramatic shapes. Towering pillars, rippling arcs, and vast cavities blown clear of gas. These processes both destroy and create. They disperse gas in some places while compressing it in others, triggering the birth of new stars. Another striking example is the Eagle Nebula, made famous by the Hubble Space Telescope's image of the Pillars of Creation. These towering columns of gas and dust, each several light-years tall, are active sites of star formation. At their tips, small clumps of dense material called evaporating gaseous globules are collapsing under gravity, soon to ignite as newborn stars. The name Pillars of Creation is no poetic exaggeration. They are literally sculpting and giving rise to new stellar systems. Over time, radiation from nearby hot stars will erode the pillars away, but by then many of the stars they nurtured will have already emerged into the wider galaxy. The process of starbirth begins in the coldest, densest regions of these clouds. When a pocket of gas becomes dense enough, its own gravity begins to pull it inward. As it collapses, the material at the centre heats up, forming a protostar. This is a delicate stage, when the young star is still shrouded in its birth cocoon of dust and gas, visible only at infrared wavelengths. Over thousands to millions of years, the protostar gathers more material from its surroundings, growing in mass. When the temperature and pressure in its core become high enough, hydrogen fusion begins, and the star officially joins the galaxy's stellar population. The environment of a stellar nursery is far from static. Radiation and winds from nearby massive stars can blow away gas, carving shapes and triggering new waves of star formation. Supernova explosions can also play a role, sending shockwaves through the cloud that compress the gas in certain regions, kick-starting the birth of more stars. This constant push and pull, destruction feeding creation, is part of what makes these regions so dynamic and visually striking. Dust plays an important role in these nurseries, not only in shaping their appearance, but also in protecting delicate new stars from harsh radiation. Without dust, the intense ultraviolet light from massive stars could strip away the material that smaller stars need to form planets. In a way, the dust acts as both a shield and a sculptor, preserving the conditions necessary for new worlds to emerge. Over time, as the nursery's gas is used up or blown away, star formation slows and eventually stops. The young stars drift apart, no longer bound to the place of their birth. Many will travel for millions or billions of years through the galaxy, carrying with them the chemical fingerprints of their origins, fingerprints that astronomers can detect in their light, allowing us to trace a star's ancestry back to long-vanished nebulae. It is worth remembering that our own sun was once born in such a place, about 4.5 billion years ago. The gas and dust from which it formed had already been enriched by earlier generations of stars, giving rise to the heavier elements that would become the planets, the oceans, and eventually life. In this way, stellar nurseries are not just the birthplaces of stars, but also the cradles of potential life, seeding the galaxy with the raw ingredients for countless worlds. To drift through a stellar nursery would be to move through a place of constant transformation. You might see vast curtains of glowing gas lit from within, dark tendrils silhouetted against the light, and distant flashes from the formation of new stars. The scale would be overwhelming. Even the smallest details would span distances greater than the space between our sun and its planets. And yet, despite their immensity, these nurseries operate on the most basic of principles. Matter gathers, gravity pulls, and from darkness light is born. In the end, the beauty of stellar nurseries is not only in their colours and shapes, but in their purpose. They are the workshops of the galaxy, endlessly recycling gas and dust into new stars, new planets, and new possibilities. Without them, the Milky Way would be a far dimmer, quieter place, a galaxy without the constant heartbeat of creation. Every star in the Milky Way has a life story, and while those stories vary wildly depending on a star's mass, they all follow the same basic arc: birth, maturity, and eventually an ending that can be quiet, spectacular, or downright catastrophic. Stars are not static pinpricks in the night sky. They are living, changing engines of fusion, each on a clock that ticks far slower than anything in our everyday experience. A star's life begins in the cold embrace of a molecular cloud, where gravity gathers gas into a dense knot. Once enough material collects and the core becomes hot and dense enough, hydrogen atoms begin fusing into helium. This fusion releases energy that pushes outward, perfectly balancing the inward pull of gravity. This is the main sequence stage, and for most stars it is a time of stability. Our Sun, for example, has been in this phase for about 4.5 billion years, and will remain so for several billion more. Think of it as the star's career years: productive, predictable, and not prone to sudden drama. But even the most stable career eventually runs into changes. For stars, this is when the hydrogen in their core runs out. Without the constant fusion to push outward, gravity starts to take over, squeezing the core and heating it further. In a medium-mass star like the Sun, this extra heat ignites a shell of hydrogen around the core, while the core itself begins fusing helium into heavier elements like carbon and oxygen. The outer layers expand dramatically, and the star swells into a red giant. You might think of this as a stellar midlife crisis, a change in size, a new outer appearance, and a shift in energy output. Though, instead of buying a sports car, the star simply engulfs nearby planets. For low-mass stars, this phase is relatively gentle. The red giant sheds its outer layers into space, creating a planetary nebula, a glowing shell of gas that can be hauntingly beautiful. What remains at the centre is a white dwarf, a dense, Earth-sized core that will slowly cool over billions of years. These white dwarfs are the quiet retirees of the galaxy, no longer fusing elements but still glowing with the heat of their long careers. Massive stars, however, have a much more dramatic ending. When they run out of hydrogen, they burn through helium and then move on to fuse progressively heavier elements: carbon, neon, oxygen, silicon. Each stage happens faster than the last until iron builds up in the core. Fusion of iron does not release energy, and without outward pressure, the core collapses in a fraction of a second. The result is a supernova, an explosion so powerful it can briefly outshine an entire galaxy. In a supernova, the star's outer layers are blasted into space at tremendous speeds, scattering elements like carbon, oxygen, calcium, and iron across light years. These are the same elements that make up planets, oceans, and even the calcium in our bones. It is not just poetic to say we are made of stardust. It is quite literally true. Every atom heavier than hydrogen and helium was forged inside a star and sent into space by one of these cosmic endings. The remains of a massive star depend on its mass before the explosion. If the core left behind is between about 1.5 and 3 times the mass of the Sun, it becomes a neutron star, a city-sized object of such density that a teaspoon of its material would weigh billions of tons. Some neutron stars spin rapidly and emit beams of radiation, appearing to us as pulsars. These cosmic lighthouses sweep their beams across the galaxy with clockwork precision, some spinning hundreds of times per second. If the core is even more massive, gravity overwhelms everything, and a black hole forms. Here, matter collapses to a point of infinite density, wrapped in an event horizon from which nothing, not even light, can escape. While black holes sound like the villains of the stellar world, they are simply the natural result of gravity doing its job under extreme conditions. Not all stellar deaths are as final as they sound. In some binary systems where 2 stars orbit each other closely, the death of one can lead to an ongoing drama. A white dwarf can pull matter from its companion, and if enough builds up it can trigger a sudden burst of fusion on its surface, a nova. This explosion is not strong enough to destroy the star, and it can repeat many times, like a cosmic fireworks show that replays at irregular intervals. In rarer cases, a white dwarf in a binary system can accumulate so much mass from its partner that it exceeds a critical limit, leading to a thermonuclear runaway that completely obliterates it. This is a Type Ia supernova, and it is so bright and consistent in its light output that astronomers use it as a standard candle to measure distances across the universe. Even after their dramatic end, stars continue to shape the galaxy. The gas and dust thrown into space by supernovae enriches interstellar clouds, giving future stars and planets the heavy elements needed for complex chemistry. In this way, the death of one star becomes the raw material for countless others. The Milky Way is constantly recycling itself, turning the ashes of old suns into the light of new ones. In the long view, the galaxy is a tapestry woven from these overlapping life stories. Some stars live short, brilliant lives, others linger quietly for trillions of years. Some end in a whisper, others in a blast that can be seen halfway across the cosmos. But every star, no matter how humble or grand, plays its part in keeping the Milky Way alive and evolving. It is tempting to think of stars as eternal, unchanging points of light. Yet, in truth, each one is on a journey, changing slowly but inexorably with time. The night sky we see today is a snapshot in an ongoing story, one in which the cast is constantly changing, and where endings are just the beginning of something new elsewhere in the galaxy. In the grand cycle of creation and destruction, stars are both the authors and the raw material of the next chapter, each one contributing to the quiet, ongoing renewal of the Milky Way. Stars, despite their solitary appearance in the night sky, are often born in company. In the earlier stages of their lives, many stars share their birthplace, with hundreds or even thousands of siblings, bound together in what we call star clusters. These are the families of the galaxy, some tight-knit and long-lived, others more like casual reunions that eventually disperse into the wider Milky Way. Star clusters come in two main varieties, open clusters and globular clusters. While both are gravitational gatherings of stars, they could not be more different in character. Open clusters are the younger, looser associations, often found in the galaxy's spiral arms where star formation is active. They contain anywhere from a few dozen to a few thousand stars, all formed from the same giant molecular cloud. Because they are young, many open clusters are still rich in hot blue stars that shine brightly but will not live for long. Over time, these clusters tend to drift apart, their members pulled away by the gravitational tides of the galaxy. Globular clusters, on the other hand, are ancient and densely packed, containing hundreds of thousands to even millions of stars. They form a spherical shape, with stars so tightly bound that in their cores, the night sky would be ablaze with light from countless nearby suns. Globular clusters are found mainly in the galactic halo, far above and below the plane of the Milky Way, and their ages often exceed 10 billion years. They are the senior citizens of the stellar community, survivors from the early days of the galaxy, when conditions for star formation were very different. One of the most famous open clusters is the Pleiades, also known as the Seven Sisters. Easily visible to the naked eye as a small shimmering patch in the constellation Taurus, the Pleiades contains several hundred stars, though only a handful can be seen without optical aid. The cluster is only about 100 million years old, practically a newborn in astronomical terms, and is still passing through the remnants of the dust cloud from which it formed. This dust scatters the blue light of the cluster's hottest stars, creating a delicate reflection nebula that adds to its beauty. On the other end of the age and size spectrum lies Omega Centauri, the largest and brightest globular cluster in the Milky Way. Containing an estimated 10 million stars, it is so massive that it may once have been the core of a small galaxy captured by the Milky Way long ago. Seen through a telescope, Omega Centauri is a glittering swarm, its stars packed so closely together that the view becomes a sea of points, each one a sun in its own right. Its stars span a wide range of ages and compositions, hinting at a complex history of formation and evolution. The gravitational bonds that hold a cluster together are not permanent. In open clusters, the ties are relatively weak. As the cluster orbits the galaxy, encounters with passing gas clouds, other stars, and the tidal forces from the Milky Way itself gradually strip away members. Over a few 100 million years, the cluster's stars disperse into the galactic field, becoming indistinguishable from the general stellar population. If you could trace their paths backward through time, you would find them converging at the same point, their shared birthplace, but to the eye, they become strangers. Globular clusters are more resilient. Their dense cores and strong gravity can keep them intact for billions of years, even as they orbit far from the galaxy's bustling spiral arms. Still, they are not entirely immune to disruption. Over immense spans of time, gravitational interactions can cause stars to escape, and some clusters may eventually dissolve. Yet their longevity is remarkable, a testament to the conditions in which they formed and the strength of their stellar bonds. Clusters are more than just pretty groupings in the sky. They are important tools for astronomers, because the stars in a cluster all formed at roughly the same time and from the same material. They provide a controlled environment for studying stellar evolution. By comparing the different types of stars within a single cluster, scientists can determine its age and learn how stars of various masses change over time. This makes clusters something like natural laboratories, set up billions of years ago and still running their experiments today. If you could drift through the heart of a globular cluster, the view would be dazzling. Stars would be so numerous and so close that the concept of darkness would almost disappear. Instead of the black velvet sky we know, you would be surrounded by a brilliant shifting dome of light. In an open cluster, the scene would be less crowded but perhaps more colourful, with bright blue stars scattered among their cooler old companions, all still loosely bound in their shared journey around the galaxy. Eventually, though, even the closest knit stellar families part ways. Open clusters fade into the galactic background, their once bright members going on to lead separate lives. Globular clusters endure far longer, but even they cannot hold on forever in a universe that is constantly in motion. Yet the stars themselves remain, carrying with them the legacy of the place where they were born, long after the cluster itself has vanished. In this way, star clusters remind us that the galaxy is not just a collection of individual points of light, but a living, evolving community. Stars are born together, grow together, and in time scatter into the vastness, each one contributing to the endless cycle of creation and change that keeps the Milky Way alive. Space might seem like an empty void, but the truth is that the vast stretches between the stars are filled with a delicate mix of gas, dust, and energy, known as the interstellar medium. It is so thin that if you scooped up a cubic centimetre of it, you would find fewer atoms than you could count on one hand. Yet, on the scale of the Milky Way, this material adds up to an enormous mass, enough to make millions of stars. It is the raw fabric from which new stars and planets are woven, the silent backdrop against which the life cycles of stars play out. The interstellar medium, often called the ISM for short, is mostly hydrogen, the simplest and most abundant element in the universe. There is also helium, along with a sprinkling of heavier elements, oxygen, carbon, nitrogen, iron, all forged in previous generations of stars and scattered into space by stellar winds and supernovae. The gas exists in different forms. Some of it is hot and ionized, some is warm and diffuse, and some is cold and dense, hiding in molecular clouds where temperatures drop so low that atoms bind together into molecules. These cold clouds are the nurseries of new stars. Threaded through this gas is something even more intriguing: cosmic dust. Unlike the kind that gathers on your bookshelf, cosmic dust is not a grey fuzz of skin cells and fabric fibres. These grains are tiny, solid particles made of silicates, carbon compounds, and sometimes ices. A typical grain might be a fraction of a micron across, far smaller than the width of a human hair. Despite their size, they have a huge influence on how we see the galaxy. Dust grains scatter and absorb starlight, dimming and reddening it in a process called extinction. If you have ever watched the sun turn deep orange as it sinks through a hazy atmosphere, you have seen a similar effect on a smaller scale. Because of dust, the Milky Way does not appear as a perfectly uniform band of light. Dark patches, like the great rift that runs through the summer Milky Way in the northern hemisphere, are clouds of dust blocking the light of stars behind them. At visible wavelengths they appear as voids, but switch to infrared or radio observations, and they reveal themselves as rich, complex structures hiding entire regions of star formation. Dust is both an obstacle and a gift. It hides, but it also preserves, shielding fragile young stars and molecules from the harshest radiation. The ISM is not evenly distributed. In some regions, the gas is thin and spread out, with just a handful of atoms per cubic centimetre. In others, particularly in giant molecular clouds, it can be dense enough to have hundreds or thousands of particles in the same space. Even so, calling it dense by earthly standards is misleading. It would still count as a far better vacuum than we can produce in most laboratories. Yet, gravity does not care about how thin it is. Given enough time, even this tenuous gas can collapse into stars if conditions are right. The ISM also plays a crucial role in the way starlight reaches us. As light from distant stars travels through the galaxy, it passes through clouds of gas and dust that can alter its appearance. Some wavelengths are absorbed, others are scattered, and some are shifted toward the red end of the spectrum. This interstellar reddening can trick the eye into thinking a star is cooler than it really is. Astronomers have to account for these effects when studying the properties of stars, carefully correcting for the veil the ISM drapes over our view. In addition to dimming and reddening starlight, the interstellar medium glows faintly on its own. Ionized regions around hot young stars emit light as electrons recombine with atoms, creating glowing emission nebulae like the Orion Nebula. Cold clouds can shine in infrared as their dust grains absorb light and re-radiate it at longer wavelengths. In the radio spectrum, neutral hydrogen emits a telltale signal at a wavelength of 21 centimeters, allowing astronomers to trace its distribution across the galaxy. This 21 centimeter line has been a workhorse of galactic astronomy, mapping the Milky Way's spiral arms and revealing the structure of the ISM in remarkable detail. There is also a more energetic side to the interstellar medium. Cosmic rays, high-energy particles accelerated by supernova shocks and other powerful events, stream through it constantly, colliding with atoms and molecules and sometimes triggering chemical reactions. Magnetic fields thread through the ISM as well, guiding charged particles and shaping the motion of gas. Though invisible, these magnetic fields influence everything from the formation of stars to the shapes of supernova remnants. The interplay between stars and the ISM is a continuous cycle. Stars form from the gas and dust, live out their lives, and return material to the medium through stellar winds or explosive deaths. This recycled material is richer in heavy elements than the gas that formed the first generation of stars, so over time the ISM has become more chemically complex. That enrichment is what allows planets like Earth to exist. Without countless generations of stars enriching the ISM, the building blocks of rocks, oceans and life would not be available. On human timescales, the interstellar medium is almost frozen in place. Clouds drift, slowly changing shape over thousands or millions of years, sculpted by the winds of nearby stars and the blast waves of supernovae. If you could watch it in fast motion, you would see it as a fluid, dynamic ocean. Waves of gas colliding, filaments twisting under the influence of magnetic fields, pockets collapsing into newborn stars while others are blown apart by intense radiation. In the quiet spaces between stars, the ISM may seem unremarkable, but without it, the galaxy would be nothing more than a fading collection of ancient suns. It is the connective tissue of the Milky Way, binding one generation of stars to the next. In its faint glow and its deep shadows, it holds both the memory of the past and the seeds of the future, drifting endlessly through the spiral arms of our galactic home. Our sun may seem like it sits still in the sky, rising and setting with reassuring regularity, but in truth it is on a vast and unending journey around the centre of the Milky Way. Every planet, asteroid, and comet in the solar system is along for the ride, bound together by the sun's gravity as we collectively orbit the galactic core. From our perspective, this motion is invisible, but over millions of years it carries us through the grand structure of the galaxy, past spiral arms, open star clusters, and clouds of interstellar gas. The sun's path around the Milky Way is not a simple circle. The galaxy's gravitational pull comes not just from the central bulge, but from its spiral arms, dark matter halo, and the combined tug of billions of stars. Our orbit is a slightly elliptical loop that takes roughly 225 million years to complete, a single galactic year. The last time we were in our current position in the galaxy's orbit, dinosaurs were just beginning to roam the Earth, and mammals were small, unassuming creatures living in the shadows. On this long trek, the Sun moves at an average speed of about 828,000 kilometers per hour relative to the galactic center. At that pace, you could travel from Earth to the Moon in less than 20 minutes, but in the vastness of space, it still takes tens of millions of years to make noticeable progress along our route. The solar system is currently located in the Orion Spur, a minor branch of stars between the Sagittarius and Perseus spiral arms. This position is relatively calm with no overly dense star-forming regions nearby, a quiet neighbourhood by galactic standards. But our orbit is not perfectly flat within the galactic disk. The solar system oscillates up and down through the plane of the galaxy, crossing it roughly every 30 million years or so. This motion, combined with our forward travel, means that over time we drift into and out of the denser regions of the spiral arms. These arms are the hubs of star formation, filled with bright young stars, giant molecular clouds, and occasionally hazards like nearby supernovae. Astronomers estimate that we pass through a spiral arm roughly once every 100 million years. The journey through an arm is not instant. It can take tens of millions of years to cross from one side to the other. While within an arm, we're surrounded by a richer concentration of massive, short-lived stars that can end their lives as supernovae. These explosions flood nearby space with cosmic rays and high-energy radiation, which has led some scientists to wonder whether spiral arm crossings could influence life on Earth. One idea suggests that increased exposure to supernovae during these crossings could affect our planet's climate. A nearby supernova could damage the ozone layer, allowing more ultraviolet light from the Sun to reach the surface. Another possibility is that cosmic rays from such events might encourage cloud formation, subtly cooling the Earth's climate. While these are intriguing possibilities, the evidence is not yet conclusive. Geological and fossil records sometimes show patterns that could match spiral arm crossings, such as periods of mass extinction or global cooling, but the link remains speculative. Another theory involves the density of interstellar material in spiral arms. As the solar system moves through these regions, it could encounter denser clouds of gas and dust. If one of these clouds were thick enough, it might compress the outer edges of the heliosphere, the bubble of solar wind that surrounds our solar system, allowing more cosmic radiation to reach Earth. This could have long-term effects on climate, and even on the mutation rates of living organisms. Of course, not every spiral arm crossing would be dramatic or dangerous. Most of the time, the changes would be subtle and spread over millions of years, barely perceptible on human timescales. For us, the motion is a slow drift through an ever-changing star field, with the constellations shifting shape over epochs rather than seasons. Yet over the full sweep of geologic time, the solar system's path through the galaxy has been anything but static. As we orbit the Milky Way, we're also moving relative to nearby stars. The Sun's closest stellar neighbours change over time as we pass through different regions of the galaxy. A few million years ago, the nearest star was not Proxima Centauri but a different neighbour altogether. Millions of years from now, the night sky will feature constellations entirely unfamiliar to us, shaped by stars that have moved into our vicinity and others that have drifted away. Our galactic journey is not just a passive ride. It is part of the dynamic life of the galaxy. We orbit the centre, weaving between the spiral arms, sometimes travelling alongside clusters of stars born in the same region, other times moving through emptier stretches of space. The Sun's motion and the slow, gravitational ballet of all the stars helps maintain the structure of the Milky Way's disk, mixing its contents over billions of years. It is humbling to remember that our familiar solar system is just one passenger in this vast procession. The orbit we trace now is similar to the one our star has followed for over 4 billion years, carrying Earth from its fiery birth to the present day. Long after our planet's surface has changed beyond recognition, the Sun will still be moving along its slow arc around the galactic core, keeping time with the motions of countless other stars. In this way, our galactic journey is both immense and deeply personal. The Sun's orbit has been the silent stage upon which Earth's history has unfolded, from the first microbes to the rise of human civilization. And though we may never feel the motion directly, it shapes our place in the galaxy, connecting us to events on scales far larger than our own lives. We are quite literally travellers through the Milky Way, riding a star on an endless voyage around a centre we will never see with our own eyes, yet which governs our path all the same. If you could somehow weigh the Milky Way, tallying up the mass of every star, planet, gas cloud and bit of dust, you might expect to get a figure that matches the galaxy's gravitational pull. After all, mass and gravity go hand in hand, but when astronomers performed that calculation, they found something strange. The visible matter, all the stuff we can see and detect directly, accounts for only a fraction of the galaxy's total mass. The rest appears to be made of something invisible, something that neither emits nor absorbs light, yet exerts a powerful gravitational influence. This unseen majority is what we call dark matter. The earliest clues came from studying how the Milky Way rotates. If the galaxy's mass were concentrated mainly in its bright central regions, then stars farther from the centre should orbit more slowly, just as the outer planets in our solar system move more slowly around the Sun. That is exactly what Newton's laws would predict. But when astronomers measured the speeds of stars far out in the galaxy's disk, they found something unexpected. The stars at the edges were moving just as fast as those much closer to the core. The only way to explain this was to conclude that the galaxy's mass is not concentrated solely in the visible matter. Instead, there must be an enormous amount of additional mass spread throughout and beyond the disk, forming a vast, roughly spherical halo that envelops the Milky Way. This halo cannot be made of ordinary matter, stars, gas, planets, because we would be able to detect it in some form of light. Whatever it is invisible, interacting with normal matter only through gravity. Dark matter's quiet hold is not unique to the Milky Way. The same pattern of flat rotation curves appears in other galaxies as well, suggesting that dark matter is a fundamental component of the universe. In fact, measurements of the cosmic microwave background and large-scale galaxy distributions suggest that dark matter makes up about 85% of all matter in the cosmos. Ordinary matter, the stuff that makes up you, me, the Earth, and every star you have ever seen, is only the small remainder. In the Milky Way, the dark matter halo extends well beyond the visible edge of the galaxy, possibly out to a distance of several 100,000 light-years. This halo provides the extra gravitational pull that keeps the stars in the outer disk from flying away into intergalactic space. Without it, the Milky Way would not be able to hold itself together in its current form. In this sense, dark matter acts as a cosmic scaffold, shaping the galaxy's structure and influencing its evolution over billions of years. What, then, is dark matter actually made of? That remains one of the greatest mysteries in science. It is not composed of the same particles that make up ordinary matter, protons, neutrons, and electrons, because those particles would interact with light and other electromagnetic radiation. Instead, dark matter must be made of something that interacts gravitationally, but is otherwise almost entirely invisible to us. Physicists have proposed a number of candidates. One possibility is that dark matter consists of exotic particles such as WIMPs, weakly interacting massive particles, that are heavy but interact so rarely with normal matter that they pass through planets and stars without leaving a trace. Another idea is that it could be made of axions, hypothetical ultralight particles that would behave more like a field than individual particles. There are even suggestions that dark matter might involve entirely new physics, perhaps particles connected to forces we have not yet discovered. Despite decades of effort, direct detection of dark matter has proved elusive. Sensitive underground detectors have searched for signs of WIMPs colliding with ordinary atoms, with no confirmed results. Astronomers have looked for indirect hints, such as radiation from dark matter particles annihilating each other. But so far the evidence remains inconclusive. It is a cosmic game of hide and seek, in which the hiding side has an almost unfair advantage, yet even without knowing its exact nature, we can see dark matter's fingerprint everywhere. It shapes the way galaxies cluster together in space, influences the bending of light in gravitational lensing, and governs the formation of large-scale structures in the universe. In the Milky Way, it determines the overall gravitational landscape through which the Sun and all other stars move. Without it, our galaxy would spin apart, and its history would have been very different. One of the intriguing aspects of dark matter is that it does not clump into small-scale structures the way normal matter does. Gas clouds can cool, collapse, and form stars, but dark matter does not appear to do this. Instead, it remains spread out in a diffuse halo, with only the gravitational influence of normal matter marking where it lies. This means that while the Milky Way's luminous features, the spiral arms, the bulge, the clusters, are dynamic and ever-changing, the dark matter halo is more like a stable framework, quietly holding the whole system in place. For all its importance, dark matter remains stubbornly out of reach of our senses. It is a reminder that the universe is far stranger than it appears. We live our entire lives immersed in a sea of matter that we cannot see or touch, yet which outweighs everything visible by a large margin. The stars that seem so dominant in the night sky are, in the bigger picture, just a glittering decoration on an invisible stage. Perhaps someday we will discover exactly what dark matter is, and its name will change from a placeholder for our ignorance to a label for something concrete. For now, it remains one of the most humbling features of our galaxy, a silent, unseen presence that binds the Milky Way together, shapes its motion, and reminds us that most of what exists lies beyond the reach of our eyes. The Milky Way may be enormous, but it is not alone. Like a grand city in space, our galaxy has a collection of smaller companions, satellite galaxies that orbit within its gravitational sphere of influence. These neighbours are not mere bystanders. They interact with the Milky Way in subtle and sometimes dramatic ways, exchanging streams of stars, gas, and dark matter. Among them are some of the most famous and easily visible galaxies in the night sky, along with others that are faint and elusive. The two best-known companions are the Large Magellanic Cloud and the Small Magellanic Cloud, often referred to simply as the Magellanic Clouds. These irregular dwarf galaxies are visible to the naked eye from the southern hemisphere, appearing as faint, misty patches against the stars. Early European explorers named them after Ferdinand Magellan, whose circumnavigation of the globe in the 16th century brought them to the attention of Western astronomy, though indigenous peoples of the southern hemisphere had been familiar with them for countless generations. The Large Magellanic Cloud, or LMC, lies about 163,000 light-years away, while the Small Magellanic Cloud, or SMC, is a bit farther at roughly 200,000 light-years. Despite their modest sizes, the LMC is about 1/10 the mass of the Milky Way. They are vibrant places of star formation. The LMC is home to the Tarantula Nebula, an enormous stellar nursery where massive stars are being born at a rapid pace. The SMC, while smaller and more irregular in shape, also contains active star-forming regions, as well as remnants of past supernovae. Both Magellanic Clouds are connected to the Milky Way by streams of gas, the most famous being the Magellanic Stream, a ribbon of hydrogen gas that stretches across more than half the sky. This stream is thought to have been pulled from the clouds by the Milky Way's gravity, a sign of the ongoing tidal interactions between these galaxies. In turn, the clouds themselves appear to be orbiting each other while also orbiting the Milky Way, creating a complex gravitational dance that has likely played out for billions of years. Closer to home, though much harder to spot, is the Sagittarius dwarf spheroidal galaxy. Discovered only in the 1990s, this small, elongated galaxy is in the process of being torn apart by the Milky Way's gravity. It lies on a polar orbit around our galaxy, passing through the Milky Way's disk multiple times over the past few billion years. Each pass strips away more of its stars, stretching them into long, looping streams that wrap around the Milky Way like a faint stellar scarf. These tidal streams are visible in detailed sky surveys and serve as a clear example of how larger galaxies grow by absorbing their smaller neighbours. The Sagittarius dwarf is not alone in its fate. Astronomers have discovered other faint dwarf spheroidal galaxies around the Milky Way, many of which also show signs of tidal disruption. Some are so dim that they contain only a few tens of thousands of stars, spread over hundreds of light years, with their dark matter halos doing most of the work of holding them together. Others are richer in gas and young stars, though these tend to lose their gas quickly once they fall into the Milky Way's gravitational grasp. Tidal interactions are a fundamental part of galaxy evolution. When two galaxies pass close to each other, their mutual gravity distorts their shapes, pulling out long tails of stars and gas. In the case of a massive galaxy like the Milky Way and a much smaller dwarf galaxy, the larger one's gravity can completely unbind the smaller, adding its stars to the halo or disk. These stellar streams can remain visible for billions of years, slowly mixing with the rest of the galaxy, but retaining a coherent path that astronomers can trace. The Magellanic Clouds themselves may eventually face such a fate. Current models suggest they are on a long-term trajectory that could lead to their gradual merger with the Milky Way, though the exact timing is uncertain. When that happens, the gas they carry could fuel new waves of star formation, much as other minor mergers have done throughout the galaxy's history. The Sagittarius dwarf is simply further along this process, a preview of what can happen when a smaller galaxy ventures too close to a giant. One reason these satellite galaxies are important to study is that they provide clues about the Milky Way's dark matter halo. The orbits and tidal disruptions of these satellites depend on the distribution of mass, both visible and dark, in our galaxy. By mapping the paths of stellar streams like those from the Sagittarius dwarf, astronomers can refine their models of the Milky Way's gravitational field, giving us a clearer picture of the unseen structure that shapes its evolution. From a human perspective, there is also something compelling about these galactic neighbours. The Magellanic Clouds hanging in the southern sky remind us that even galaxies live in communities, bound together by gravity and history. The faint arcs of tidal streams are like fossil trails, preserving the record of past encounters that shape the Milky Way we see today. In time, the Milky Way will continue to collect and absorb its smaller companions, growing slightly larger and more massive with each encounter. The stars from these galaxies will become part of the halo, or mingle with the stars of the disk, their original homes forgotten except by those who trace their origins through careful observation. The Magellanic Clouds, the Sagittarius dwarf, and the many other faint dwarfs scattered around the Milky Way are not just bystanders, they're active participants in the galaxy's ongoing story, each one contributing to its growth, its structure, and its quiet, unending motion through the cosmos. Trying to map the Milky Way from our position inside it is a bit like trying to sketch the layout of a vast forest while standing in the middle of the densest patch of trees. No matter which way we look, our view is crowded with stars, gas and dust, and there is no way to step outside for a better perspective. The scale alone is daunting. Our galaxy is about 100,000 light-years across, yet we can see only a few thousand light-years in detail before dust clouds begin to obscure our view. For centuries, astronomers relied on visible light to chart the sky, plotting the positions of stars and nebulae as they appeared to the eye or through telescopes. These early efforts revealed the band of the Milky Way stretching across the night sky, but they could not show its full structure. The reason was simple: interstellar dust absorbs and scatters visible light, especially along the crowded plane of the galaxy, creating dark lanes that block our view of what lies beyond. From the ground, it was impossible to tell whether the Milky Way was a flat disk, a sphere, or something else entirely. The breakthrough came with the ability to observe the sky in wavelengths beyond visible light. Radio astronomy, in particular, opened a new window. Neutral hydrogen, the most abundant element in the galaxy, emits radio waves at a wavelength of 21 centimeters. Unlike visible light, these radio waves pass through dust clouds unimpeded, allowing astronomers to trace hydrogen gas across the Milky Way. By measuring the Doppler shifts of this emission, scientists could determine the motion of the gas and begin to map the spiral arms from the inside. This method, combined with knowledge of how stars and gas move in a galaxy, gave the first real outlines of the Milky Way's shape. Infrared astronomy provided another leap forward. Infrared light, with its longer wavelengths, can also penetrate dust far better than visible light. Observations in the infrared revealed millions of stars that had been hidden behind the galaxy's dusty veil, especially in the crowded regions near the center. Space telescopes like the Spitzer Space Telescope and the Wide-Field Infrared Survey Explorer allowed astronomers to map these hidden stars, filling in the blanks left by visible light surveys. In recent years, the European Space Agency's Gaia mission has transformed our view of the Milky Way yet again. Launched in 2013, Gaia has been measuring the positions, distances and motions of more than 1 billion stars with unprecedented precision. By tracking how stars shift against the background over time, a technique known as astrometry, Gaia can determine their distances to within a fraction of a percent for many stars. This has created the most detailed three-dimensional map of the Milky Way ever made. We can now see the galaxy not just as a flat chart, but as a living, moving system, with stars streaming along their orbits and clusters drifting apart over time. Gaia's data has revealed unexpected structures within the galaxy, such as vast stellar streams left behind by past mergers with smaller galaxies, and ripples in the disk that may have been caused by interactions with the Sagittarius dwarf galaxy. It has also given us a better picture of the Sun's exact motion through the Milky Way, and improved our understanding of the spiral arm's shapes and positions. Even with all these tools, mapping the Milky Way remains a work in progress. The galaxy is too large, too complex, and too full of obscuring material for any single method to capture it completely. Astronomers combine data from multiple wavelengths – radio, infrared, optical, ultraviolet, X-ray – to build a composite picture. For example, X-ray observations reveal the high-energy processes near black holes and neutron stars, while ultraviolet data highlight regions of hot young stars. Together, these views give a more complete sense of the galaxy's structure and activity. The challenge is that everything we map is constantly in motion. Stars orbit the center at different speeds, spiral arms slowly shift, and gravitational interactions reshape the galaxy over time. A map of the Milky Way is never truly finished. It is more like a snapshot in a constantly changing cosmic film. Gaia's repeated observations are helping to capture some of this motion, allowing astronomers to model how the galaxy looked in the past and how it may appear in the future. There is also the difficulty of measuring distances accurately, especially to objects on the far side of the galaxy. Even small errors in distance can distort the apparent positions of spiral arms or other features. To overcome this, astronomers use a range of distance ladders, starting with the most precise measurements of nearby stars and working outward to more distant objects by comparing their known properties. Each rung of the ladder supports the next, but every step involves careful calibration. Despite these obstacles, our map of the Milky Way has come a long way from the hazy sketches of centuries past. We now know it is a barred spiral galaxy, with a central bulge, multiple major arms, and a thin disk surrounded by a thick halo of old stars and dark matter. We can trace the paths of stellar streams, identify clusters in the halo, and measure the motions of stars across vast distances. And yet, there are still mysteries. We have only a partial map of the far side of the galaxy, obscured by the dense dust near the centre. There may be entire structures, spiral arm segments, large star-forming complexes that remain hidden from view. Future missions, particularly those that can combine infrared and radio capabilities with high precision, will help fill in these gaps. In the end, mapping the Milky Way is not just a technical challenge, it is a way of finding our place in the cosmos. We live inside a vast, complex system that we can never step outside to see in its entirety. Every improvement in our map is like turning up the resolution on a picture we've been trying to interpret for generations. With each new discovery, the Milky Way becomes both more familiar and more astonishing, reminding us that even in our own galactic home, there is still so much left to explore. Surrounding the bright starry disk of the Milky Way is a vast, faintly populated region known as the Galactic halo. Unlike the thin, pancake-shaped disk where most of the galaxy's stars and spiral arms reside, the halo is a roughly spherical cloud of stars, clusters, hot gas, and dark matter that extends far beyond the visible edges of the Milky Way. It is a place of quiet and age, where the galaxy's oldest residents drift in long, slow orbits, far from the busy stellar traffic of the disk. The stellar halo contains some of the most ancient stars in the galaxy, many of them formed more than 10 billion years ago. These stars are generally metal-poor, in astronomical terms, as metals are any elements heavier than helium, because they were born before multiple generations of stars had enriched the galaxy's gas with heavier elements. Their light carries the chemical fingerprint of a much earlier universe, one that had not yet been thoroughly seeded with the products of stellar evolution. In that sense, halo stars are living fossils, holding clues to the Milky Way's earliest formation and growth. Scattered through the halo are globular clusters, those dense, spherical gatherings of hundreds of thousands of stars. Each cluster is a self-contained island of ancient suns, bound tightly by their mutual gravity and often older than the galaxy's spiral arms themselves. From the ground, they appear as compact, fuzzy patches in the night sky, but through a telescope they resolve into dazzling swarms of points, so tightly packed in their cores that stars would be only a fraction of a light-year apart. Many of these clusters orbit far above or below the galactic plane, tracing paths that carry them deep into the halo's remote regions before swinging back toward the inner galaxy. The origins of the halo's stars and clusters are varied. Some were likely part of the Milky Way from its earliest days, coalescing from the primordial clouds of gas that formed the first structures in the galaxy. Others were stolen from smaller galaxies that the Milky Way absorbed over time. When a dwarf galaxy ventures too close, the Milky Way's gravity can strip it apart, scattering its stars into the halo and sometimes leaving behind faint looping streams that mark the remnants of its orbit. These streams, along with the halo's most metal-poor stars, tell the story of a galaxy built through mergers and gradual accretion. But the halo is not just a collection of old stars and clusters. It is also home to a huge, diffuse reservoir of hot gas. This gas is invisible to the naked eye but detectable in X-ray and ultraviolet observations, where it appears as an extended corona surrounding the galaxy. Its temperature can reach into the millions of degrees, heated by the combined effects of supernova explosions, stellar winds, and the galaxy's own gravitational compression. The halo's hot gas is thought to be a major component of the Milky Way's missing baryons, ordinary matter that is hard to detect but must exist to match cosmological predictions. And then there is the most mysterious part of all, the dark matter halo. While the stars and gas in the visible halo extend perhaps a few 100,000 light-years from the galactic centre, the dark matter halo is thought to reach much farther, possibly as far as 1,000,000 light-years or more. This enormous, invisible structure accounts for most of the Milky Way's mass, shaping its gravitational field and holding the galaxy together. Without the dark matter, halo's stabilizing influence, the stars in the outer disk would drift away, and the spiral arms would lose their structure. The halo's dark matter is not arranged in neat, uniform layers. Simulations suggest it may be clumpy, shaped by the same merger events that built the stellar halo. Streams of stars torn from dwarf galaxies could be accompanied by streams of dark matter, each one a faint ghost of a long-gone system. While we cannot detect these dark streams directly, their gravitational effects on the motions of stars may one day reveal their presence. Life in the halo, if one can call it that, is very different from life in the disk. The density of stars is much lower, meaning the night sky from a halo star's perspective would be sparser, with fewer bright neighbours and the Milky Way's disk stretching across the sky as a distant glowing band. The orbits of halo stars are elongated and inclined in all directions, unlike the nearly circular paths of stars in the disk. Many of them pass far from the galactic centre before looping back in, their journeys taking hundreds of millions of years. For astronomers, the halo is more than just an outer shell. It is a record of the galaxy's formation and growth. Each ancient star, each globular cluster, and each faint tidal stream is a clue to the events that shaped the Milky Way over billions of years. By studying the motions, compositions, and distributions of halo stars, scientists can reconstruct the mergers and interactions that built our galaxy, much like an archaeologist piecing together the history of a city from its oldest ruins. Despite its importance, the halo remains one of the least understood regions of the Milky Way. Its faint stars are difficult to study in detail, and its hot gas is so diffuse that even sensitive instruments struggle to measure it. Mapping the extent and shape of the dark matter halo is even harder, requiring careful modelling of the motions of stars and satellite galaxies. Yet each new observation adds to the picture, revealing that the halo is not a static shell but a dynamic, evolving part of the galaxy's ecosystem. Ultimately, the halo is both a relic of the past and a framework for the future. It preserves the earliest chapters of the Milky Way story, while quietly holding the galaxy together in the present. It stretches far beyond the stars we can see, linking the visible Milky Way to the larger cosmic web of galaxies and dark matter that fills the universe. In its quiet expanse, the halo reminds us that our galaxy is not just a flat disk of stars, but a vast layered structure, one whose outermost reaches still hold more questions than answers. If you were to imagine all the planets in the Milky Way laid out before you, you might quickly realise there is a problem. There are far too many to keep track of. Current estimates suggest our galaxy could host well over 100 billion planets, perhaps even more. That is not a poetic exaggeration. It's a conservative calculation based on what we've been able to observe so far. For every star, there could be at least one planet on average, and since many stars host multiple worlds, the real tally may run far higher. The mind easily jumps to Earth-like planets, but in reality, the Milky Way's planetary population is astonishingly diverse. There are hot Jupiters that whirl around their stars in just a few days, frozen ice giants orbiting far out in the cold, and rocky worlds baked to a crisp by their suns. Some planets may be entirely covered in oceans, others may be barren deserts where the surface is a sea of lava. The galaxy is a planetary artist with an almost absurd range of creative designs. The discovery of these worlds is one of the more remarkable scientific achievements of the last few decades. Until the early 1990s, we had no confirmed detections of planets beyond our own solar system. The first came in 1992, and surprisingly it was not found around a star like the Sun but orbiting a pulsar, a dense, rapidly rotating neutron star. Since then, the number of known exoplanets has exploded into the thousands, thanks to a combination of patient observation, technological innovation, and a little bit of luck. One of the most effective tools in this hunt has been the transit method. Imagine staring at a star and noticing a tiny periodic dip in its brightness. That faint dimming could be a planet passing in front of it, blocking a small fraction of the light. By measuring the size, timing, and shape of these dips, astronomers can infer a planet's size, its orbital period, and even hints about its atmosphere. This method is responsible for the lion's share of planet discoveries, largely thanks to dedicated space telescopes like Kepler and TESS. Another powerful technique is the radial velocity method. As a planet orbits its star, its gravitational pull tugs gently on the star, causing it to wobble ever so slightly. This wobble shifts the star's light spectrum back and forth in a predictable pattern, redder when the star moves away from us, bluer when it moves toward us. By measuring these shifts with incredible precision, astronomers can detect planets and estimate their masses. Direct imaging is also possible, though it is extremely challenging. Stars are blindingly bright compared to their planets, so astronomers must use specialized instruments and clever techniques to block out the starlight, revealing the faint glow of a planet beside it. So far, only a small number of exoplanets have been captured this way, but those images are breathtaking. Actual photographs of alien worlds light years away. There is also the method of gravitational microlensing, which takes advantage of a quirk of Einstein's general relativity. When a star passes in front of a more distant star, its gravity bends and magnifies the light of the background star. If the foreground star has a planet, the planet's gravity can add a distinctive blip to this magnification. This method can detect planets that are otherwise too faint or too far from their stars to be seen by other means. Despite all these methods, what we have found so far is only the smallest fraction of what exists. Most of our detections are biased toward planets that are relatively large, orbit close to their stars, or are in systems favourably aligned for our instruments. Small rocky planets like Earth are still much harder to detect, especially if they orbit at distances that would place them in their star's habitable zone, the region where liquid water could exist on the surface. It is also worth remembering that the galaxy's planets are not confined to neat orbits around stars. Some worlds, known as rogue planets, drift freely through space after being ejected from their home systems. These lonely travellers are invisible in most cases, detected only when they happen to pass in front of a distant star, and reveal themselves through microlensing. Estimates suggest there could be as many rogue planets in the Milky Way as there are stars, if not more. The variety of planetary systems we have observed so far has already challenged our assumptions. For years, astronomers thought our solar system might be a typical template. Small rocky worlds close in, giant planets farther out, and stable, nearly circular orbits. Instead, we have found systems where giant planets skim the surfaces of their stars, systems packed with multiple planets in tight orbits, and worlds with eccentric paths that carry them from freezing darkness to blistering heat in a single year. The galaxy, it seems, has far more imagination than we gave it credit for. The hunt for exoplanets is not just about counting them, it is about finding the places where life might exist. While we cannot yet visit these worlds, new technologies are allowing us to begin studying their atmospheres. By analysing the starlight that filters through a planet's atmosphere during a transit, scientists can search for molecules like water vapour, methane, and oxygen. The detection of certain chemical combinations could one day point to biological activity, though interpreting such signs is far from straightforward. Future missions promise to transform our understanding even further. The James Webb Space Telescope has already begun taking its first detailed measurements of exoplanet atmospheres, and planned observatories will have the sensitivity to detect smaller and cooler worlds. There is even hope of eventually imaging Earth-like planets directly, perhaps seeing blue oceans and white clouds from dozens of light years away. And yet, for all our progress, we have truly only skimmed the surface. The number of planets we know of is a tiny fraction of the likely total, and the diversity of those yet to be found is beyond imagining. The Milky Way is not just a galaxy of stars, it is a galaxy of worlds, each with its own history, its own weather, its own potential for life. Somewhere out there, among the billions of planets we will never see, there may be worlds with sunsets we could never dream of, storms unlike anything on Earth, and perhaps even oceans where life drifts in alien currents. The search continues not just because we want to know what is out there, but because every discovery reminds us that our planet, precious as it is just one chapter in a vast and ongoing galactic story. When most people think of black holes in the Milky Way, their minds leap straight to the supermassive one lurking at the galactic centre. But scattered quietly across the galaxy are countless smaller black holes, stellar mass black holes, formed when massive stars end their lives in spectacular supernova explosions and collapse under the weight of their own gravity. These black holes are the cosmic leftovers of stars many times heavier than the Sun. When their nuclear fuel runs out, the core collapses so completely that not even light can escape. What remains is a point of infinite density, a singularity, surrounded by an event horizon, the invisible boundary beyond which nothing can return. The result is a silent, invisible object moving through space, detectable only by the way it interacts with its surroundings. Astronomers estimate there could be millions of stellar mass black holes in the Milky Way. Most wander unseen, giving away no clues to their presence. If a black hole is not actively feeding on nearby material, it blends into the darkness, indistinguishable from the void itself. But when conditions are right, these otherwise hidden objects can reveal themselves in striking ways. One of the most reliable methods of finding them involves binary star systems. If a black hole orbits a normal star, it can pull gas from its companion. As the gas spirals in, it forms an accretion disk, a whirling, flattened ring of superheated material glowing brightly in X-rays. These X-rays pierce through the surrounding darkness, making the system detectable to space-based telescopes. Cygnus X1, one of the most famous stellar mass black holes, was discovered in just such a way. Located about 6,000 light-years away, it was once the subject of a friendly bet between physicists Stephen Hawking and Kip Thorne. Thorne bet it really was a black hole, Hawking bet it was not. In the end, Hawking conceded and mailed Thorne a subscription to Penthouse as payment, because scientists have a sense of humour too. Another detection method comes from observing the motion of stars themselves. Even if a black hole is completely dark, its gravity still exerts an unmistakable pull on any visible companion. By carefully tracking the star's orbit, its speed, shape, and the way it shifts over time, astronomers can deduce the presence of an unseen massive partner. If the calculated mass is too great to be a neutron star and too small to be a supermassive black hole, the conclusion is clear: they have found a stellar mass black hole. Gravitational microlensing also offers a way to spot them. When a massive object passes in front of a distant star, its gravity bends the starlight, temporarily magnifying it. Unlike most microlensing events, which last for weeks or months, those caused by black holes can linger for much longer because of their greater mass. In recent years, this method has uncovered several strong candidates for isolated black holes drifting through space. Incredibly, we can now also detect stellar mass black holes when they collide and merge with one another. These cataclysmic events send ripples through space-time, gravitational waves, which were first directly observed in 2015 by the LIGO detectors. The chirp of such a merger encodes information about the masses of the black holes, their spins, and the energy released in the collision. Some mergers involve black holes many times the mass of the Sun, producing more energy in a fraction of a second than all the stars in the observable universe combined, and yet almost all of it escapes as gravitational waves rather than light. Not all stellar mass black holes have the same origin story. While most are born from collapsing massive stars, some may result from stars that began their lives in dense stellar clusters, where repeated interactions and collisions gradually built up enough mass for a collapse. Others could be the remnants of the very first generation of stars, enormous, short-lived giants composed almost entirely of hydrogen and helium that formed when the universe was still in its cosmic infancy. If such ancient black holes still roam the galaxy, they are relics of an era we can barely imagine. For all our progress, it is striking how few of these black holes we have actually found compared to how many we believe exist. The vast majority remain invisible, drifting silently through the galaxy like cosmic ghosts. Some may pass relatively close to our solar system over the span of millions of years, their gravitational influence subtly tugging on comets or altering the paths of small objects in the outer reaches of the Oort cloud. The odds of one wandering close enough to cause real trouble are astronomically low, but the thought does lend a certain drama to the calm emptiness of interstellar space. These stellar mass black holes are a reminder that the Milky Way is not just a place of light and creation, but also of endings, or perhaps transformations. The material that once formed a brilliant short-lived star is now locked away in an object so extreme that space and time themselves bend around it. Yet the story does not truly end there. Matter falling into a black hole can unleash energy that shapes its surroundings, from jets of high-speed particles to intense radiation that can influence star formation nearby. Far from being simple cosmic vacuum cleaners, these black holes are participants in the ongoing evolution of the galaxy. And somewhere, out in the quiet reaches between the stars, there are many more waiting to be found. If we can learn to listen for their silent signatures in the fabric of space itself. The Milky Way, for all its graceful spirals and glittering stars, is the product of a long and often violent history. To picture its origins, we need to go back over 13 billion years, to a universe that was still warm from the Big Bang and far smaller than the one we see today. In those early moments, matter was not yet arranged into galaxies. Instead, the cosmos was filled with vast clouds of hydrogen and helium, laced with tiny traces of lithium. The simplest elements forged in the first minutes after time began. Over time, the force of gravity began to gather this diffuse gas into denser clumps. Where these clumps grew large enough, their own gravity pulled in more matter, and the first stars were born. These earliest stars were enormous and short-lived, burning hot and bright before ending their lives in titanic supernova explosions. Those explosions seeded their surroundings with heavier elements, oxygen, carbon, iron, creating the raw materials needed for planets, life, and everything we know today. In the cosmic neighborhood where the Milky Way would eventually take shape, these first small galaxies began to merge, drawn together by their mutual gravity. The early Milky Way was not the grand, orderly spiral we see now, but a chaotic, growing cloud of stars, gas, and dark matter. Mergers were frequent and often violent. When two galaxies collided, their stars passed mostly unscathed. The spaces between them are so vast that direct collisions are rare, but their gas clouds slammed into each other, triggering bursts of star formation. This process of galactic cannibalism is not just a dramatic phrase. It is the very mechanism by which large galaxies grow. The Milky Way likely swallowed dozens, perhaps hundreds, of smaller galaxies over billions of years. Some of these ancient victims left their mark in the form of streams of stars arcing through our galaxy's halo. These stellar streams, like the Sagittarius stream, are the remnants of once independent galaxies that were stretched out and dispersed by the Milky Way's gravity. We can still see this process happening today. The Sagittarius dwarf galaxy is currently in the midst of being torn apart and absorbed, its stars gradually becoming part of the Milky Way's outer halo. Farther out, the large and small Magellanic Clouds, our brightest satellite galaxies, are bound to us in a slow gravitational dance that will likely end with their eventual assimilation. The galaxy grows not in a single, dramatic gulp, but in many slow bites over cosmic time. Not all of the Milky Way's building blocks came from galactic mergers. Streams of cold gas have flowed in from intergalactic space throughout its life, replenishing the galaxy's fuel for star formation. Without these cosmic refills, our galaxy's star-making machinery might have sputtered out long ago. This inflowing gas keeps the spiral arms lit with new, young stars even now. The shape of the Milky Way, a barred spiral, is also a product of its history. The central bar, a long structure of stars stretching across the galactic core, may have formed from gravitational instabilities that developed as the galaxy matured. The spiral arms themselves are likely a long-lasting pattern shaped by density waves, where regions of slightly higher density move through the disk, compressing gas and sparking the birth of stars. These patterns may have been influenced or even triggered by past interactions with other galaxies. One particularly intriguing clue to our galaxy's past comes from studying its oldest stars. These ancient stars, found mostly in the halo and globular clusters, have very low amounts of heavier elements. This tells us they were born early in the galaxy's history, before generations of supernovae had enriched the interstellar medium. By tracing the ages, motions, and chemical compositions of stars across the Milky Way, astronomers can piece together the order and timing of the major mergers that built our home. The Gaia spacecraft has revolutionized this detective work. By mapping the precise positions and motions of over 1 billion stars, Gaia has revealed distinct stellar populations that seem to share a common origin. One major find, dubbed the Gaia Enceladus, or Sausage Galaxy, appears to have merged with the Milky Way about 10 billion years ago. This collision dumped a vast number of stars into the halo and may have reshaped the Milky Way's early disk, influencing the structure we see today. Even though the Milky Way feels like a stable, permanent presence in the night sky, it is still evolving. Its interactions with neighbouring galaxies continue to shape it. In about 4 billion years, the Andromeda Galaxy will approach for a head-on collision. Despite the drama implied by collision, the two galaxies will pass through each other, their stars weaving together into new patterns over hundreds of millions of years. After a long and complex merging process, the result will likely be a single, giant elliptical galaxy, the ultimate transformation of our spiral home. Our galaxy's history is written in the movements of its stars, in the ghostly streams that lace the halo, and in the chemical fingerprints of ancient stellar populations. It is a history of both creation and destruction, of building through the graceful but relentless force of gravity. Every star we see, including the Sun, is part of this ongoing story. Born from the debris of past generations, moving through a galaxy that is itself the product of countless cosmic unions. If the Milky Way could tell its own story, it would be one of quiet patience stretched across unimaginable spans of time. It began as a handful of gas clouds in a young universe, grew through countless mergers and infall of matter, and now spins serenely in the darkness, still changing in ways too slow for us to notice in a single lifetime. And like all living things in the cosmos, if galaxies can be said to live, it carries the memory of its youth in its structure, a record of the countless encounters that made it what it is today. Long before telescopes revealed the Milky Way as a sprawling collection of billions of stars, people looked up at the faint, misty band across the night sky and wove it into their stories. With no knowledge of galaxies or interstellar distances, they saw in it a trail of light with meaning, a celestial river, a road to the afterlife, or the spilled milk of a goddess. The human mind, ever eager to explain and imagine, turned this streak of pale light into a bridge between the earthly and the divine. In ancient Greece, the name Milky Way comes from the myth of Hera, the queen of the gods. One version tells that the infant Heracles, son of Zeus, was placed at Hera's breast while she slept. When she awoke and realized who the child was, she pushed him away, and a spray of her milk spattered across the heavens, forming the glowing band of stars. It is a story at once cosmic and domestic, turning a universal feature of the night sky into something born of a single intimate moment. Across the Mediterranean, the Romans inherited the Greek tales but also had their own interpretations, often associating the Milky Way with the divine realm and the souls of the dead. To them, the galaxy could be seen as a shining road, a celestial counterpart to the great roads that tied the empire together on Earth. Farther north, in Norse mythology, the Milky Way was sometimes described as the path to Valhalla, the Hall of the Slain, where warriors chosen by Odin would feast and fight for eternity. In Finnish folklore, the galaxy was called the Pathway of Birds, thought to guide migrating birds across the seasons. Even in the coldest nights of winter, these cultures found ways to see movement and life in that silent, distant glow. In Mesoamerica, the Maya viewed the Milky Way as a cosmic river, a celestial reflection of earthly waterways. The galaxy's bright bulge in the centre was sometimes envisioned as the mouth of a great crocodile or a celestial tree, with the darker dust lanes forming its branches and roots. For the Inca, the dark patches within the Milky Way were not gaps between stars but shapes of animals. The llama, the fox, the serpent, all outlined by the dust clouds that wind through the galactic core. To see such creatures in the sky required not looking at the stars themselves, but at the spaces between, a reminder that absence can be as powerful as presence. In parts of Africa, the Milky Way has been described as the backbone of night. Among the Khoisan people of southern Africa, one story tells of a girl who flung ashes from a fire into the sky, creating the glowing band of light. The ashes became stars, and the Milky Way served as a guide for hunters and travellers, ensuring they would never lose their way under an open sky. In China, the galaxy was known as the Silver River, the dividing line in one of the most beloved love stories of East Asia. In this tale, a cowherd and a weaving maid, separated by the River of Stars, are allowed to meet only once a year, when a bridge of magpies forms across the sky. This story, celebrated during the Kixi festival, weaves romance into the cosmic landscape, turning the galaxy into a symbol of longing and reunion. The Aboriginal peoples of Australia have some of the richest traditions connected to the Milky Way. In many Aboriginal cultures, the galaxy is seen not as a single image, but as a tapestry of stories. Some see it as the great emu in the sky, traced not by the stars but by the dark dust lanes against their glow. The orientation of the emu changes with the seasons, marking times for gathering eggs and other activities. Others see campfires of ancestral beings, the smoke of which drifts across the sky in the form of the galactic band. In Islamic tradition, the Milky Way has been called the straw of the sky, sometimes imagined as a pathway trodden by angels. Medieval Islamic astronomers studied its nature with great curiosity, debating whether it was made of vapour, light, or an enormous number of faint stars. Their work would later influence European astronomy during the Renaissance. Artists too have long found inspiration in the Milky Way. In European Renaissance paintings, it appears as a mystical backdrop, a reminder of the divine order of creation. The Dutch painter Aert van der Neer's 17th century nightscapes often place the soft band of the galaxy above still waters, its reflection doubling the sense of infinity. Even Vincent van Gogh, in his Turbulent Starry Night, gave a swirling nod to the great spirals of the heavens, an echo of the structure hidden in the Milky Way's faint haze. In literature, the galaxy has often been used as a metaphor for both distance and unity. Poets have likened it to a bridge between worlds, a trail of dreams, or a cosmic spill of light across the void. Modern writers, armed with the knowledge of its true nature, still find it an inexhaustible source of wonder. After all, knowing that the Milky Way contains hundreds of billions of stars has not diminished its magic. It has only deepened it. Science, in many ways, has brought us full circle. When Galileo turned his telescope to the Milky Way in the early 17th century, he found that its misty glow was indeed countless individual stars, far too faint for the naked eye. This revelation transformed the galaxy from a single ethereal streak into a vast, intricate system. Yet even with this understanding, the old names and myths remain. They remind us that before we measured light years or mapped spiral arms, we measured the galaxy in stories, shaping it to match our hopes, fears, and imagination. Today, whether one stands in a remote desert, lies on a grassy hillside, or peers from a ship's deck in the middle of the ocean, the Milky Way still stretches overhead much as it did for our ancestors. It is both a scientific marvel and a shared human inheritance, a canvas on which every culture has painted meaning. To look at it is to stand in the same place as those who came before, connected across centuries by the same ribbon of light. And in that way, the Milky Way is not just a galaxy. It is one of the oldest bridges between the human mind and the cosmos. The Milky Way may feel timeless and unchanging, but like everything in the universe, it is in motion, and it has a date with destiny. Far across the void, the Andromeda Galaxy is heading straight toward us. It is not a reckless dash, though. This cosmic approach happens at a stately pace of a few hundred kilometers per second, which, while brisk by human standards, is leisurely in galactic terms. The collision will not happen tomorrow, or even in the lifetime of our species, but in roughly 4 billion years the two great spirals will meet. This meeting will not be a quick smash and go. Galaxies are mostly empty space, so when they collide, the stars within them almost never hit each other directly. Instead, their mutual gravity weaves them into a slow and complicated dance, with orbits warped, star systems thrown into new paths, and great tides of gas and dust stretching between them like luminous bridges. The first close pass will fling long streamers of material into space, giving each galaxy ragged extensions, almost like cosmic jellyfish trailing their tentacles. The process will take billions of years to unfold. After the first encounter, the Milky Way and Andromeda will swing past one another and then be drawn back together. Each pass will strip away more of their distinct shapes, pulling the spiral arms into elongated curves before shredding them entirely. In time, the two galaxies will settle into one enormous blended structure. Astronomers sometimes call the anticipated product Milkomeda, a name that sounds whimsical but represents a truly grand object. A single galaxy with perhaps 1 trillion stars. From the perspective of an observer on a safe, stable planet somewhere within one of the merging systems, the sky will change dramatically. Andromeda, now just a faint smudge in our night sky, will swell over millions of years into a vast, bright presence. It will dominate the heavens, its spiral arms clearly visible without a telescope. As the collision continues, stars from Andromeda and the Milky Way will intermingle, and the night will be studded with strange new patterns. The familiar constellations we know today will be lost in the shuffle, replaced by entirely new arrangements. While the idea of a galactic collision may sound catastrophic, it is unlikely to threaten life on any given planet simply because of the enormous distances between stars. The real drama will be in the gas and dust. When the Milky Way and Andromeda's interstellar media collide, the compression will trigger waves of intense star formation. Newborn stars will blaze into being at an accelerated pace, lighting up the merging galaxies like a celebratory display. Massive, short-lived stars will end their lives as supernovae, enriching the surrounding space with heavy elements, the raw ingredients for planets, life, and future generations of stars. Over time, as the two galaxies complete their merger, the wild bursts of star formation will calm down. The gas reserves will be used up or heated so much that they cannot collapse into new stars. The once lively spirals will fade into the smoother, rounder form of an elliptical galaxy, dominated by older, redder stars. It will be a quieter, more sedate place, glowing steadily but without the same vibrant arms that once defined both the Milky Way and Andromeda. The collision is not just a two-player event either. The local group, our small neighbourhood of galaxies, will likely be affected as well. Smaller galaxies like the Magellanic Clouds may be drawn into the gravitational chaos and eventually merged into the new supergalaxy. Even the more distant members of our group may find their orbits altered over time. The result will be a reshaped cosmic community, bound together in a new gravitational equilibrium. Astronomers can model this future using both observations and computer simulations. By measuring the motions of Andromeda's stars and the Milky Way's own movements, they can rewind and fast-forward the cosmic clock, tracing the galaxy's past interactions and predicting their future embrace. These simulations produce breathtaking visualizations, spiral arms stretching and twisting, galactic centres passing like ships in the night before curving back toward one another and eventually merging into a vast golden sphere. From a more philosophical perspective, the eventual merger is a reminder that nothing in the universe remains static. The night sky as we know it is a fleeting arrangement, just one frame in a long cosmic story. Our galaxy has already grown through past mergers, swallowing smaller galaxies, absorbing their stars and weaving their remnants into its own structure. The coming union with Andromeda is simply the next act in that ongoing tale. In the far future, perhaps intelligent beings will gaze up from worlds orbiting stars born of this collision and wonder about their galaxy's origins. They might trace the arcs of ancient stellar streams, find subtle differences in chemical composition between one group of stars and another, and piece together the history of two once distinct spirals that became one. Their myths and stories about the sky will be shaped by a galaxy that, to them, has always been a single, immense home. And the idea that it was once two might seem as distant and abstract as the idea of galaxies themselves once was to us. In the meantime, the Milky Way continues its slow approach, Andromeda drifting ever closer across an unimaginably vast gulf. The collision is inevitable, but it is also patient, moving on a timescale that makes even the longest human history look like a blink. Knowing this future awaits does not diminish the beauty of the Milky Way today. If anything, it adds another layer of wonder, reminding us that our galaxy is alive with motion, change, and a destiny written in the quiet pull of gravity. When you look up at the Milky Way on a clear, dark night, it is almost impossible not to wonder if someone, somewhere out there, is looking back. Our galaxy is vast, home to hundreds of billions of stars, each potentially orbited by planets. Among those planets, how many might host life? And among those worlds where life exists, how many might have developed intelligence, technology, and perhaps even curiosity about the universe just as we have? In the early 1960s, an astronomer named Frank Drake decided to turn this question into something more concrete. He developed what became known as the Drake equation, not a precise calculation, but a framework to help think about the factors involved in estimating the number of communicative civilizations in our galaxy. The equation multiplies together a series of terms: the rate at which new stars form, the fraction of those stars that have planets, the average number of planets that could be habitable, the fraction of those that actually develop life, the fraction of life-bearing planets that produce intelligent beings, the fraction of intelligent civilizations that develop detectable technology, and finally the average lifetime of such civilizations. Each of those terms is uncertain, and some are wildly so. For a long time we did not even know whether most stars had planets. That has changed dramatically thanks to space telescopes like Kepler and TESS, which have shown us that planets are common, so common that in our galaxy alone there may be more planets than stars. Estimates now suggest that in the Milky Way there could be tens of billions of potentially habitable planets. That sounds promising, but the other terms in the Drake equation remain more elusive. We have exactly one confirmed example of life, Earth, so our statistical base is rather limited. Still, the Drake equation gives scientists a way to organise their thinking and to update estimates as new data comes in. For instance, the discovery of life elsewhere in our own solar system, perhaps in the subsurface oceans of Europa or Enceladus, would drastically change our understanding of how easily life arises. Finding even microbial life in two separate locations within one solar system would suggest that life might spring up wherever the conditions are right. The question becomes more complex when we start thinking about intelligent life. Civilizations that develop advanced technology might be rare, or they might be common but short-lived. Technological species could destroy themselves, lose interest in exploration, or simply fail to communicate in ways we can detect. The lifetime of civilizations is one of the most critical and most speculative parts of the Drake equation. If civilizations tend to last for millions of years, the galaxy might be teeming with signals. If they usually fade within a few centuries, the odds of two existing at the same time and noticing each other drop sharply. This is where the search for extraterrestrial intelligence, or SETI, comes in. Since the mid-20th century, scientists have used radio telescopes to listen for signals that might originate from other civilizations. The idea is straightforward. Radio waves can travel vast distances through space with relatively little interference, making them an efficient way to communicate. SETI programs scanned patches of the sky, listening across a range of frequencies for anything that stands out as non-random, repeating, or otherwise artificial. So far, we have not detected a confirmed extraterrestrial signal, but the search is far from over. The galaxy is enormous, and we have only listened to a tiny fraction of it. SETI is not limited to radio. Optical SETI searches look for laser pulses, sharp, bright flashes that could be used to send data across light years. Other researchers explore the idea of looking for waste heat from advanced civilizations, reasoning that even enormous energy collectors or space-based industries would radiate heat in the infrared. The hunt for what scientists call techno-signatures is broadening, guided by the understanding that alien technology might not look anything like ours, but would still have detectable side effects. Alongside the search for technology, there is the search for life's chemical fingerprints, biosignatures. This is where missions like the James Webb Space Telescope are transforming the field. By analysing the light from distant planets as it passes through their atmospheres, astronomers can detect the presence of molecules like oxygen, methane, or water vapour. Certain combinations of gases, especially those that would not remain stable without continual replenishment by life, could hint strongly at biology. For example, a planet with both oxygen and methane in its atmosphere would be suspiciously lively, since those gases tend to react with each other and would need constant production to persist. Finding such a biosignature would not confirm intelligent life, but it would be an extraordinary discovery, proof that we are not alone in a biological sense. From there, the question would naturally shift to how common intelligence is among living worlds, and whether life elsewhere tends to follow paths anything like our own. One of the humbling realities of the search for life in the Milky Way is that distance is both our friend and our obstacle. The vastness of the galaxy means there could be countless civilizations without us ever hearing from them, simply because signals fade over light years, or because we have not yet looked in the right place. On the other hand, distance also offers the tantalizing possibility that we are not just a lonely anomaly, that our story is one of many playing out across the spiral arms. It is worth noting that not all scientists agree that we should be broadcasting our presence. The idea of active SETI, deliberately sending powerful signals into space to announce ourselves, is controversial. Some argue that any civilization capable of hearing us is likely to be advanced enough not to pose a threat. Others point out that we cannot know the intentions of unknown civilizations, and that caution may be wise. For now, most of our contribution to the galactic conversation is accidental. Radio, television, and radar signals leaking into space, growing fainter as they expand outward. Whether the galaxy is buzzing with civilizations or silent except for us, the search itself is deeply valuable. It pushes technology forward, inspires new generations of scientists, and forces us to think about our place in the cosmos with a wider perspective. The act of looking up and wondering connects us to something much larger than ourselves, and even if we never find an answer, the question will continue to shape our imagination. The Milky Way is a grand stage, and we are one of its countless possible players. Somewhere out there, on a world circling a distant star, there may be beings asking the same questions, scanning their skies, and wondering if anyone else is listening. In that sense, the search is not just for life. It is for connection, for understanding, and for the reassurance that across the vast dark there is a shared experience of existence. And perhaps one day that long silence will break, We have been drifting together through a galaxy that is both our home and a vast frontier of unknowns. Along the way, we have crossed luminous arms of stars, paused in clouds where new suns are born, lingered near ancient clusters, and glanced toward a black hole so massive that it anchors the entire Milky Way. We have touched on the quiet reign of dark matter, the delicate arrangement of stellar neighborhoods, and the shimmering bridges between our galaxy and its companions. Each of these moments is just a glimpse, a brief window into the grand architecture of something we can never see in its entirety from where we stand. The Milky Way is not merely a place on a map of the cosmos, it is the framework of our existence. Every breath you take, every drop of water, every atom in your body was assembled here over billions of years of stellar alchemy. Stars that lived and died long before the sun scattered the elements that would one day form planets, oceans, forests, and people. We often talk about the galaxy as if it is out there, but we are not outside of it. We are woven into its structure, moving along with it, part of the same ongoing story. We have seen how spiral arms wind gently around the core, a kind of galactic heartbeat where new generations of stars flicker into life. We have passed through regions where space is not empty, but filled with fine threads of dust and clouds of gas, the raw material of creation. We have learned that most stars are not giants or blazing supernova candidates, but quiet red dwarfs, steady companions that burn slowly for trillions of years, holding on to their planets in peaceful solitude. At the centre, hidden behind veils of dust, lies a supermassive black hole, Sagittarius, a star. It is an object of paradox, an invisible well of gravity shaping the movement of millions of stars, yet it only rarely announces itself. Out in the wider disk, stellar nurseries bloom, clusters form and eventually drift apart, and planets, possibly billions upon billions of them, circle their suns, each with its own potential story. We have seen that the galaxy is more than just what meets the eye. Dark matter holds it together in a gravitational embrace, unseen but measurable. The halo extends far beyond the bright spiral arms, a reminder that the Milky Way is larger, older, and stranger than it might seem. And we've learned that it is not alone. Satellite galaxies and faint stellar streams are constant companions, some falling in, others just passing through. Our own sun is not fixed in place. It orbits the galaxy once every 230 million years, carrying Earth and all its life through changing neighbourhoods of space. This journey may influence our history in ways we do not yet fully understand, perhaps even shaping the conditions for life over geological timescales. The thought that our planet has circled the galaxy multiple times since its formation is both humbling and quietly astonishing. We have looked forward toward a time when the Milky Way will merge with the Andromeda Galaxy. In a few billion years, the two will combine into something entirely new, reshaping the night sky into a grand, chaotic dance of stars. For now, we are in a calm moment between past collisions and future transformations, free to contemplate the galaxy as it is, a living, evolving system, and we have reflected on the possibility of life beyond our own world. The Drake equation, the search for biosignatures, and the long listening watch of SETI remind us that we are part of a galaxy full of possibilities. Whether we are one among many or entirely alone is still unknown, but the search connects us to something far greater than ourselves. In the end, our voyage through the Milky Way is not just about mapping spiral arms or cataloguing stars. It is about recognizing that our story is inseparable from the galaxy's story. Every quiet dawn on Earth, every storm over the oceans, every human achievement, all of it unfolds against the backdrop of a vast, rotating island of light. We are passengers, participants, and products of this galactic home, sharing in its beauty and its mystery. The next time you see the Milky Way stretching across a dark sky, remember that you're looking not at a distant band of stars, but along the plane of our own home, a place of unimaginable scale, shaped by forces both gentle and violent, ancient and ongoing. And somewhere within it, on a small blue planet, we are watching, learning and dreaming, knowing that our journey through it is far from over. As we drift toward the quiet end of our journey tonight, imagine the Milky Way not as something distant, but as the very stage on which your entire life unfolds. Every moment you have ever lived has taken place within its spiralling arms. Every breath you take carries atoms once born in the hearts of ancient stars. The galaxy is not just the scenery of the universe, it is the thread from which you are woven. We have spoken of its immensity, but the truth is that our minds can barely hold the scale. 100,000 light years from side to side, home to hundreds of billions of stars, each perhaps with worlds of its own. And yet, in that unimaginable vastness, we occupy a small, warm corner, a planet just the right distance from its star, orbiting peacefully in the Orion Arm. In the language of the cosmos, we live in a comfortable neighbourhood, a quiet lane in a city that never sleeps. The Milky Way is a place of contrasts. It is both ancient and constantly renewed. Stars are born in clouds of gas and dust, live their luminous lives, and eventually give their elements back to space. New stars form from those same ingredients, keeping the galaxy alive in an endless cycle. Somewhere, right now, a star is igniting for the first time, while another is collapsing in a spectacular finale, events separated by thousands of light years, yet part of the same grand choreography. Even the empty space between stars is not truly empty. It holds the fine dust that softens starlight, the wisps of gas that will one day collapse into suns, the invisible particles of dark matter holding the galaxy together in their silent grip. Out beyond the bright spiral arms lies the halo, a realm of old stars, ancient clusters, and faint streams marking the remnants of galaxies long absorbed into our own. And then there is motion, constant, quiet motion. We orbit the centre of the galaxy at an average of about 500,000 miles per hour, yet we do not feel it. Stars, planets, gas clouds, all are moving in a complex dance guided by gravity. Over millions of years, these orbits carry us through new regions of the galaxy, each with its own history and conditions. The Milky Way itself drifts through space toward the Andromeda Galaxy, a journey that will end in a vast, graceful merger billions of years from now. It is humbling to realise that the galaxy has been here for more than 13 billion years and will remain long after our species is gone. And yet, within that immense timescale, this moment is ours. We live in a brief, beautiful interval, able to look up at the night sky and not just see light, but understand it. To know that those distant points are suns, that the soft band overhead is our galactic home viewed from within. Perhaps most of all, the Milky Way is a reminder of perspective. When life feels overwhelming, remember that our problems, though real and important, exist within a universe so vast it defies comprehension. That is not to say our concerns do not matter, but rather that there is comfort in knowing we are part of something greater. The same galaxy that contains black holes and supernovae also contains us, thinking about our place within it. If you ever find yourself beneath a truly dark sky, take a moment to let your eyes adjust, and then look for that pale, hazy river of light. It is not just a pretty feature of the night. It is the cross-section of our home, a glimpse along the disk of stars that cradles our existence. Every photon that reaches you from it has travelled across light years of space, through clouds of dust past planets, and around other stars, to finally meet your gaze. In a way, the galaxy is always with you, whether you notice it or not. It is in the atoms of your body, in the sunlight that warms your face, in the gravity that keeps our planet steady on its path. You're not simply living in the Milky Way, you're of it. And just as the stars have their cycles, so do we. Our lives begin, unfold, and eventually end. But in doing so, we pass along our own tiny contribution to the galaxy's ongoing story. So as we close this quiet voyage together, I hope you carry with you the sense of calm that comes from knowing your place in the grand design, not as an outsider looking in, but as a participant in a vast, beautiful system. Keep looking up, both literally and figuratively. Let the galaxy remind you to stay curious, to keep seeking beauty, and to understand that even in the darkest stretches of space, light is never truly gone. And perhaps tonight, as you drift into sleep, you might imagine yourself among the stars, gently moving with the Milky Way on its endless path through the universe. After all, whether you think of it or not, you're already along for the ride,